Okay, today, parametric equations, completely new stuff. Well, it's new in how we address it. You know what? Advanced functions is such a limiting course. It just feels like there's handcuffs on the whole time. It feels like, how can this possibly be what math is like in real life? Well, it's not. It's like introductory math. It's like, we're getting there. We're almost there. 11U was so painful. And then 12U was like, well, I'm starting to see what math might actually be like in the real world. This course definitely does that. We're going to let go of some of the rules and some of the barriers that stopped us from doing real math. And this lesson moves towards that. It's called parametric equations. Oh, I won't have a controller here. Okay. Well, this picture tells you more than you might think. Way back when, in grade 9, we talked about that curves couldn't curve back on themselves. We said, oh, this is not allowed. We said you can't do stuff like that on DT graphs. We all agreed that wasn't the way to go. Later on we said functions can't do this, they can't loop back. And we gave examples to explain why you can't loop backwards on yourself like this. We said, oh, well, if you're doing an experiment in physics, at a certain time you can't be at two different heights. And everybody went, yes, that sounds about right. And everybody played along. No one really questions that. Well, that's nonsense. There's lots of things that can loop back on themselves. Just imagine instead of a ball flying through the air, you're talking about a fly flying around. Well, this fly he can go wherever he wants. He's not restricted by things. But the variables have changed now. It's not time and height. Time and height, those rules still apply. You can't loop back on yourself and have two different heights at a certain time. But you can go around like this and have a certain y value at two different times. Hey, you can loop back that way. So that's where this is changing. See, this function that's on the screen here, there's a lot going on here. It seems real simple, but there's a lot going on here. At each time, the x and y values are recalculated, and you can have whatever x and y values you want at any particular t value. See, it just opens things up a little bit. Why did we make it difficult like that? Well, actually, we were trying to make it easy. Through grade 9, 10, 11, 12, we were trying to analyze functions. Tried to make it simpler and go, okay, let's just talk about ones that don't loop back on themselves. Very restricting, but math was easier. Now that you're better at math, we can open things up a little bit. And you'll see, not much new math-wise here, actually today, but a new idea that we can do whatever we want. You're lost, maybe. On the first slide, you should be. It should just be, the only thing you should get out of this first slide is, oh, maybe we can do whatever we want. But we're going to need another variable. T is putting its brain out here. And it's a great choice for variable. Time. At different times, whatever this is, has all sorts of different x and y values. This is right on the edge of being able to go x, y, z. Real world now. Not x and y. X, y, z. Whatever we're talking about, the fly or the spaceship or whatever can just fly through the air. Go wherever you want. We're almost there. So we're getting there. We're on our way to real world. In the past, we've described graphs mainly using equations in which y is given as a function of x. These equations are example of Cartesian equations. Okay, this word comes up on the test. So I want you to do something. I'm going to circle it on the screen. I think you should highlight it, because this definition, I'm not going to ask this definition on the test. I'm not going to say, okay, what's a Cartesian equation? That's not what I said. What I asked on the test is I said, here, make the Cartesian equation. On one question, I said, make the Cartesian equation. And if you don't know what that sentence means, you'll be out of luck on that question. But if you know what it just means get it back to y's and x's. And at this point in the lesson, you may be like, what do you mean, get it back to y's and x's? Isn't it always y's and x's? No, things are going to go haywire here. When I say Cartesian, back to what you're used to, y's and x's. Examples of Cartesian equations. Y equals x squared, an old friend. Cartesian equation, y's and x's. Y equals sine x, an old friend. Cartesian equation, and this big mess, rational expression, x over x squared minus 1, vertical asymptotes, horizontal asymptotes, all that kind of stuff. But a Cartesian equation, y's and x's. I'll say something silly like I'll say, oh, y equals x over x squared minus 1. That's a simple situation. Well, it's not simple at all. That's insane. It's got vertical asymptotes, horizontal asymptotes. In advanced functions, this was a big deal to try and analyze and graph one of these big things. Okay? It is simple in this way, though. It's just y's and x's. Okay? So when I say simple like that, I'm not trying to imply it's easy. It's just y's and x's. That's all we got to deal with, all we got to worry about. Some curves, however, are difficult. Well, actually, that should go one step further. Sometimes it's impossible to put it just with y's and x's. That's a part of the story we left out. We acted like all through 11U and advanced functions, oh yeah, we can do anything. We were very restricted. We had very specific curves we could do and all sorts of stuff that we couldn't do. Couldn't even begin to touch it. And that's why it didn't feel real. It's like, what? This is what happens in the real world, really? No, we're getting there. We're on our way. So it says difficult here. Some are impossible to represent using equations of this form. It's better than that. They're difficult or impossible to represent with y's and x's, but easy in this new way we're going to do. So it's a new way of thinking today, but it's going to make a whole bunch of stuff easier. An example of a function, such a function that's virtually impossible to use y's and x's, is called the cycloid. The cycloid looks like a bunch of semicircles, but it's not. The best way to imagine how a cycloid gets created is, just imagine for a second that there's a piece of gum stuck to the tire of your bicycle. That piece of gum goes through an interesting journey. It goes around on your bike, and to you, on your bicycle, if you were on your bicycle looking at this piece of gum on your tire, it would just go around in a circle. You say, well, that's not complicated. In fact, your brain might even scream, wait, we did circles. We can do this. We did circles in grade 10 for a minute, didn't we? What was that all about? There was some kind of equation for circles. I'll get to it by the end of the lesson. But it doesn't just do that. So for someone that's watching you drive by on your bicycle, the piece of gum is doing this. It's going around in circles, but it's going down the street as well. Y's and x's? Good luck. Yeah, physics doesn't have any great answers for this right away, because it's not just a nice parabola going through the air. Okay? You're not going to be responsible for the equation of the cycloid. In a minute, I'm going to develop it. And hopefully your brain's going to explode and go, what are you doing? Where are you getting all this stuff from? You're not responsible for it, this chapter at all. I want to show it to you so you can see the power of what I'm showing you today. So here's a visualization of it. Can you see the piece of gum on the tires you go by there? And it goes on a very strange journey. And this, although it might look like a semicircle, it's not. It's not shaped that way. It's more elongated than that. You say, well, it's an ellipse. Oh, it's worse than that. It's not just an oval. It's multiple ovals. And only half of multiple ovals. If I said, okay, come up with an equation with y and x, you'd be a long time trying to come up with this whole curve like that. Okay? That's not that weird a situation, actually. Like, in the world, that's not that weird. A piece of gum on a tire going down the street. That's not crazy, crazy stuff. But math-wise, it would stump what we've got in our bag of tricks so far. Curves like the cycloid are more easily handled with both x and y defined in terms of a third variable t called the parameter. You'll often see this parameter, and I'm going to switch colors here because I didn't like how that came out. You'll often see this called a dummy variable. And by dummy variable, we mean it's actually sort of meaningless in the whole thing. We're just plugging the values in there to make something happen. It might have felt like this with y equals mx plus b sometimes. Back in grade 9, when you graphed a line, you might have subbed in different x values to get the shape of the line. Later on, you learned about m and b, and you didn't have to make a table of values. But when you made a table of values, you put in 1 and 2 and 3, and you went, oh, it's a straight line. And you took your ruler and drew a line through it. But someone besides you might not use the same x values as you. They might use -1, -2, -3 and get the same line. And that's what we mean by dummy variable. It doesn't matter what you sub in, probably. you'll get the same thing when you put it in. If you don't like that, someone could put in 0.1, 0.2, 0.3, and they'd get the same thing. So the variable isn't tied to exactly what's happening. You can use whatever you want. Yeah? You'll see lots of that coming up. This dummy variable, or this parameter, you can use whatever you want, really. Maybe that's an exaggeration. It's not whatever you want. There's lots of good choices, is what I mean to say for the parameter. Here's the equation for the cycloid. 2 levels of understanding. First level of understanding of the equations of a cycloid. You look at this and go, well, that's not that complicated, actually. That's the first level of understanding, going, oh, we can make an equation of a cycloid that isn't all that complicated. Good. I'm feeling better about this situation, that a cycloid can be represented easily. Second level of understanding. Can you see how the given pair of equations defines the graph? No. Not even a little. We haven't given you any of the capabilities it would take to be able to do this and see that these equations represent the cycloid. Hold on. That's a lie. We could just sub numbers in. You could sub in 0, pi over 2, 3 pi over 4, pi. You could just do all that subbing and do all the graphing, dot, 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 and you get the curve, and you go, oh, I can do it. Sort of a basic rudimentary understanding of the whole situation. Go, yeah, I guess I see it works. But who came up with this? Where did that actually come from? This is the part you're not responsible for, even though you should be able to follow most of it. Okay? And I want to open up, it's just weird how it's happened with us, because advanced functions was so weird to us in how it was taught, that little pieces of the puzzle might be missing, and they're important pieces of the puzzle for this. Okay? But no freaking out. This is completely, can you stick with me all the way through it and go, oh, I see it. Because you have the math to follow me here. Yeah? I'm going to switch screens for a second. We'll keep the annotations. We're going to need active inspired here. Oh, blank screen. Very good. Now you get to find out how good I can draw. I've got the circle tool, but I'm going to try and do it on my own. Here I go. How'd I do? Look like a circle? Oh, this pen's arguing with me. Good. Starting point. Then I'm going to get the gum out. My gum's going to be green for today. You see the gum there? Okay. Now, when developing things like this in math, then we go, okay, we want a picture of the start of the situation, which we don't really care about the start. It's just to establish what the heck is going on. And then this is at some time later. Switch pens here. So sometime later, I got to draw a very, very good diagram of the second one so you can see what's happened. Need another beautiful circle. Okay, come on, pressure's on. Beautiful circle. I was thinking that the fact that I'm recording this is going to keep me from getting distracted and telling side stories, but I'm not sure it's going to. At some point, I'm not going to care. One of the videos that Mrs. Todd made in the summer was a long video, and I was supposed to be outside with the kids, and she was inside making the video. And then a kid got away on me and ran in and started talking to her. So the video, it's like a 47-minute video, at about the 32-minute mark, you can hear this whole conversation between her and Bennett on the video. So she apologized for it, and all the kids were like, no, it was great. And in the middle of it, it sort of woke them up, all of a sudden Bennett comes on the video. Okay. See, I'm getting distracted already. I didn't even make it through one good video. Okay, here we go. So now the gum's up here, yeah? You see where it's gone from? It started here, yeah? Light green over here. It started here, and it went. Do you see the cycloid started developing? This gum, as it went as the tire turned, the gum went. Ooh. Oh, I can see the panic in some of your eyes already. Like, I already don't like this diagram. No, you're not responsible for this. You're responsible in this part of it. So just follow along and go, oh, I sort of get that. And every bit of math I'm going to use is math you have. Okay? Putting it all together, well, okay, that's troublesome, yeah? Okay, now what I'm going to try and do, and see if this works, is take all that and give myself some, oh, that went well. Some room to maneuver. I got to do some math underneath here. All right, now what we're actually trying to come up with is an equation for x. What color am I going to go down here? I'm going to go black down here. X and y. That's what I'm really after. Now keep in mind, the whole idea of parametric equations is that we'll have an x equation and a y equation in terms of another variable now. It's not y equals x anymore. It's x equals something and y equals something. Okay? Let's talk about the x for a minute. Two things have gone on. This tire has rolled down the street. And this tire has turned through an angle theta. There's theta. That's how much the tire has turned. The gum started at the bottom and it rotated up to that spot there. So this tire has turned an angle theta. What that means is, how much is it rolled across the ground here? I can do this distance right here. And again, what I'm really hoping, this part of the lesson will be a success. If what I write next, your brain goes, oh, I sort of remember that. Yeah? That'll be enough. Not like I could do it. No. More like, oh, that stuff. Oh, yeah. Okay? So what we want to know is how much of that arc length of the circle has rolled across the ground. This A equals r theta. Does it pop in just for a minute? Just even a little bit. Like, oh, yeah. A equals r theta. Radians. Radians coming back just a little bit. I know it wasn't taught in the perfect form. It was all online. Maybe you just were in survival mode and you wrote down the answers you had to, and you checked the book while you were doing your assignment, and you called somebody or texted somebody. I get it. A equals r theta is how far that thing's moving along. But that's not the x value of the gum. Do you see? This is why this situation is so difficult. The x value of the center of the circle isn't the x value of the gum. The gum's going around like this at the same time. It's over there a little bit. Now I got to draw this part carefully. I'm going to use my little green lines. No, I don't use this green. I'm going to use orange. Tell me if you can see the orange. Can you see the orange there? The little tiny triangle in there. I'm going to blow that triangle up in just a minute. And there's another angle in there. So here's the orange triangle here. Are you with me? That's that triangle right there. It's got sides, which I will call B and C. Now the only thing I got to set here is how big the tire is. And I got to tell you, it doesn't matter how big the tire is. It's sort of irrelevant on this. It'll come up later. I could put the radius of the tire at 5, or at 10, 55. And it won't really matter as far as the math is concerned. It'll just be a multiplier in all this. So just for ease of use, and you'll see this a lot in math coming up, is just the first time through, I'm going to make the radius of the tire 1. If I can do it with 1, if I can do the math with 1, I can do it with 27 or 44. It won't matter. Yeah, we'll worry about changing it later. So this radius of the tire is 1. Now there's a new angle I've created in here. And I'm going to call that angle, maybe I'll call that angle, I don't want to use something I've already used. I don't want to use another Greek letter. I can still remember my profs using Greek letters and me getting confused by the Greek letter. So I don't want it to be about a Greek letter. So I'm going to use the angle D, capital D for that angle in there. So it's not about Greek letters. I'm going to do a little work on this right angle triangle, which seems like a waste of time at this point, but it's going to be huge. I'm going to say, oh, okay, that means the sine of this angle D equals opposite over hypotenuse. You see, there's that 1. If it was a different radius, it would be a different number, no big deal. And then cos of this angle D will be B over 1. So what I get is sine D equals side C, and cos D equals side B. Good. This will be handy in just a minute, okay? I got all that stuff available. How would you know to do all that? If you were developing this the first time, you wouldn't know to do all that until later. I'm just getting it ready to hopefully the next part of the lesson flows a little better. Let's talk about the x value of the gum. The x value of the gum is r theta. That's the motion of the tire down the street. It's gone r theta. But the gum is going around, and so it's not on the center of the tire. It's moved back this much by this amount here, this C here, which I just figured out was sine D. Best part of this section of the lesson coming right up. You're like, well, that's great. Now you got a million letters on the screen, actually. I can fix it up a little bit. One is the radius of the circle. I set the radius of the circle. It's not r. What did I make the radius of the circle? Just checking if you're with me. 1. Okay, that's 1 theta. And d, you're like, well, you've introduced a new variable there. I'm like, I know, but check this out. What's the relationship between theta and d? They're right connected, aren't they? They're together in a straight line. Okay, let's go back to what the grade 9s would say. What does theta and d add up to in degrees? 180. Okay, we got to be radians. On this pathway, we are radians the rest of the way. You're like, I hated radians. You're killing me with the radians. I never really understood it. I'm like, well, you better grow up, huh? Because we're going to need radians. So what is the relationship between these two angles in radians? Do you remember? Pi. Good. Okay, so if that's, you're not responsible for that just yet, okay, in this course. But if you get that out of this lesson, pi equals 180 degrees, that's a good step forward. You know, to reminding yourself what radians are all about. Pi radians is 180 degrees. What that means is this d is pi minus theta. Now it's all thetas. More from advanced functions coming here. 2 angles subtracted inside of sine. We didn't do much on this. As I was building the lessons in advanced functions, I was like, I don't know how much I can do of this online like this. I've got them next year anyways. I'll bring it in there. But do you remember the trig toolbox? Trig toolbox had something like this in it. Sine of x minus y equals sine x cos y minus cos x sine y. Let me hold it up so you can... You remember this? I didn't put too much pressure on it. Because at the time it would be like, what is this for? Does this even really matter? Our very first problem in calculus, there it was. We need it. Okay, I just saw the panic in somebody's eyes. Remember, when I started this example, you're not responsible for this in this chapter. What I'm trying to establish is the importance of all the stuff you got in advanced functions and using it at some point, and how this simple example, really, gum on a tire, turns into some really great mathematics. Great. I called it great. Intense, we'll call it, yeah? Great. So here we go. X equals theta minus sine pi cos theta minus cos pi sine theta. Let's see if I plug that all in right. Sine pi cos theta, yes, minus cos pi sine theta. Yeah, it's all right. Big moment. It's going to finish off x here. What's the sine of pi? You know what we lose in the middle of this? My facial expressions. Okay. Without my mouth, I think the nod's going to be the new thing. You notice people are nodding a lot more? It used to be you just smile at somebody. If you don't want to have to talk to them, you see them always smile at them. I'm smiling underneath my mask, you can't tell. Now everybody's like nodding. There, I gave you enough time. Brad, what is it? 0. Oh, he's got it, folks. Sine pi is 0. Cos pi is -1. It's right from the graph, so sine and cos. And so what I end up with here is x equals theta minus, that's -1, that's 1. So that's negative 1, that's positive. So I get sine theta minus sine theta. There's the x value. Theta minus sine theta. I use thetas instead of t's. Irrelevant. It's a dummy variable. It's just a parameter. It's just to decide how. Here's where you might really understand dummy. I walked up there and I said, you know what? Let's call this angle theta. I didn't have to call it theta. Could have called it t. It's a dummy. It doesn't matter in the question. It's not the height or anything like that. It's not the x, the y. It's whatever I want it to be. Okay. On a scale of 1 to 10, give yourself a number on how well you followed that. A 5 being, well, I don't think I can do all that math, but the individual pieces I recognized. I recognized all that. You give yourself a 5 if you're like, oh, everything he said seemed familiar to me. Whatever number you give yourself, let's do the y and see if it gets better. And if that happens, I got to tell you, it's a good university strategy. A prof teaches something, you're like, I didn't get that at all. You go, okay, that's fine. Give myself a 1 on that. Does the next example, and you go, oh, now I go on 2. If that happens, no matter what your numbers are, you're going to be fine. Prof does an example and you're a 1. Next example, you're a 0. Now you can panic, because you're not on the map at all. You text me, or you go to your TA, or you do whatever you have to do. It's going to happen. Why? The y value is r, which is just 1, plus this d here, this b on the side of the here, and the b was cos t. Oh, no fancy stuff there. Except this is d's, and this is theta. How is d related to theta? Take a look in there. The two of them add up to, your brain screams 180, and then you go, oh no, radians, pi, and so I get cos pi minus theta. And then I get my trig toolbox out. Okay, here's the thing, before you freak out. In this course, if you're going to need some of this memorized for a test, I will pre-warn you. Every test that it comes up that you need something off this list, I'll write them on the board. Okay? It comes up so little in this course that I'm quite willing to give it to you, and you'll know it's coming. All right? So no freaking out about this. Like, I don't have that memorized. You'll have what you need off here whenever you do need it. I'm not sure we'll carry one of these around, but I'll write what you need to on the board. Okay? So you really just get it out and you go, okay, cos pi minus theta. Where is it? Okay, so that's cos pi, cos theta. Is it plus or minus? Cos minus. Oh, minus is plus. Isn't that interesting? Sine pi. Sine theta. The nice thing about this is it simplifies nicely. Cos a pi. I'm going to kill time for a minute and let everybody process and see if cos pi can come back up in your brain. Do we know what cos of pi is? Let's see. Cosine starts up here. By pi, it's down here. We're at -1. Sine of pi, let's see, sine starts here. By pi, it's back down to 0 again. That's a 0. And I get nothing there, so 1 minus cos theta. How'd I do? 1 minus cos t. They use t. It's a dummy. It doesn't matter. Oh, whatever you want. Okay, back to here what I was saying on this slide, though. There are multiple ways to understand these equations. The first level, which I do want you to understand, is, oh, those are pretty simple. I could sub into those. I could put numbers in there, and I could get that. I could draw this curve. Second level, that whole screen you just saw, which you're not responsible for just yet. And by just yet, I mean, that's more of a first physics course, first university course type example, yeah? Using all the math you've seen before to come up with something like that. Now, profs are nuts, though. Like, nuts. How long did it take to do that? Was that 15 minutes, that example? They'll do it in 5. You think my writing's bad? Wait till you see a prof's writing. Huh? They'll just scribble it. Do not panic. Get down what they say, and you're like, I didn't get that at all. Go watch a YouTube video, ask the TA, they explain it a little slower, and you go, oh, that's the sine formulas from that. Oh, yeah. It's easy to get lost in the details. No freaking out, yeah? Especially first year. First year university like grade 9. Who cares what marks you get? Doesn't matter. It's irrelevant. Just learn the program. Get your feet under you. I know grade 12 there's a lot more pressure. We need big marks here. But first year university, it doesn't really matter. Back to here. Back to, where was I? There. Can you see how the given pair of equations defines the graph? Sort of. I sort of see where that's all coming from now. Equations of this form are called parametric equations. So what should you have got from this lesson so far? Oh, we can do a whole different sets of curves if instead of going y equals x, getting stuck to y equals x, we go x equals some equation in t's, which should look familiar. T minus sine t, that's not that weird. If I asked you to sub into it, you shouldn't be that freaked out by it. And y equals 1 minus cos t, it's also in terms of stuff that you've seen before. Parametric equations are also useful for describing relations that are not functions. We're not doing them yet, but these type of shapes, which one, are difficult to do with y's and x's, and two, they're not even functions, with parametric equations, they're actually pretty straightforward. It's not really a big problem to come up with these type of shapes. Now, do we care about these type of shapes? Is this the picture of something going around? Yeah, actually. There's actually a situation you could set up like a tire with a piece of gum on it, where you get these kind of shapes. And it just gives us more power to deal with things that are more real world. We're on our way to dealing with whatever phenomenon is going on out there. Just imagine for a second the equation of u going through the universe. There's lots going on here. Maybe you're walking down the street. You're walking down the street on a planet that's spinning around a sun that's spinning around the center of the galaxy. There's a lot going on there. But with parametric equations in x, y, and z, we've got a chance. Got to get these things figured out if we're going to send probes out to Pluto and Mars and Venus. They work all this stuff out. Here's the formal definition. Definition of a parametric curve. If x and y are given as functions, x is a function of t, y is a function of t. All these letters serve to confuse you. Just go back. All they're saying is x will be some equation with t's, y will be some equation with t's. That's all that's going on there. Over an interval of t values, the set of points x, y equals f at t, g at t defined by these is called a parametric curve. The equations are parametric equations for the curve. The variable t is called a parameter. We often use t because it represents nicely as time. Instead of an angle that the thing's moving through, it's how much time has passed for the gum to go down the street. The domain for t is called the parameter interval. If t is defined, the point f at a, g at a is the initial point of the curve. What? If I took t equals 0, times 0 and subbed into here, I'd get 0 minus 0. I get x value 0. When I put in t equals 0 here, I get 1 minus cos 0 would be 1. 1 minus 1 is 0. I'd get the initial point. All they're saying is, if you sub in the lowest possible t value, you'll get the initial point. Almost like, duh, of course that's what would happen. The first t value should give the initial point. Yeah? Sometimes these words make it seem more complicated than it is. And then the last point of the interval, whatever the last t values, will give the end point. Back to my drawing, that gum going down the street, there'll be a time where it starts and there'll be a time where this whole procedure ends. And you can just specify that. When we describe a curve using parametric equations and a parameter interval, we say that we have parametrized the curve. That's a question on the test. You don't know how to do it yet, but I'll say parameterize these curves. And what I mean is come up with the equation and come up with the interval. You're like, I don't know exactly what you mean. I'm going to do a zillion examples. When I finish here, all I'm going to do is examples after this. The equations and the interval consist of a parameterization of the curve. Example, here we go. Consider the following parametric equations. We went complicated, let's go back to simple for a second. Now, I want to warn you about something too. In the middle of this, we might do some parameterizations on parabolas, lines, where you go, can't we just do this with y's and x's? And the answer is yes, we absolutely can just use y's and x's. You're like, well, why are we doing these with parameters then? To get ready for things like cycloid. Yeah, let's do familiar things first, and then we'll work our way up. Yeah? So, look here. Consider the following parametric equations. X equals t squared minus 2t, y equals t plus 1. And the interval here is negative infinity to infinity. It means you can have any t values you want, or as big or as small as you want. Other questions will have a restriction on that domain, and you'll see why when we get there. Use a table of values to sketch the curve. Is it all in your note? Good, good. We're past having to sit here and sub all these things in. I hope that you can type these numbers in, but let me go through what's happened. They chose some t values here. It said negative infinity to infinity. We're hoping that with a bunch of t values, we can get an idea on the shape, and we don't have to sub in every value from negative infinity to infinity. You did this on table of values, maybe when you're learning about parabolas. You'd sub in negative 3 to 3, you get a curve like this, and you go, oh, I get it now. You didn't have to sub in negative 50 and 50 to get the idea, okay? And that's what we're doing here. So I took negative 2, and I subbed it into x, and I got 8. And I subbed it into y, and I got negative 1. Now I've got an x and y value I can use to graph this thing. Then I took negative 1. How did I choose negative 1? I don't know, it's just a dummy variable. I just kept throwing numbers in there, hopefully getting enough things to get the information I wanted. Are these enough? I don't know. Let's just see what the curve looks like when I do it. You won't know until you plug enough in. Right? I subbed in negative 1 into x and got 3. I subbed, let me just try something here for the sake of people that will be watching this. I mean, you're all here today, but laser pointer. Oh, this will be on your video now. Yeah? So I subbed in negative 1 into the x, and I subbed in negative 1 into the y, and I got 3 comma 0, another point for my curve. And I just kept subbing in these t values. So at this point, you're like, okay, so with a parametric equation, I've got t values that I sub into both equations this time to get my x and y. For a parabola like this one is, you might be like, can't we just go back to y's and x's? I'm like, absolutely. No one would ever really do parabolas with parameterization. We're just practicing, because cycloids are too hard. Yeah? Right now, you'll get there. And if I plot all those x and y values, 8, negative 1, 3, 0, 0, 1, negative 1, 2, 0, 3, 3, 4, 8, 5. Oh, it is a parabola, but take a look at it. Sideways parabola, which was against the rules a little while ago. You know, I was like, oh, that's not a function. But now in parametric curves, it's no problem. No big deal. Of course something can go through this pattern. Imagine a fly flying through the air. Of course it can go like this. Well, in this case, it went like this, didn't it? That's the direction it went. It started at 8, negative 1, and it came this way and went around. This is very close to describing paths of spaceships through space, you know, as they go out and around planets and so on. Like, this is very close to being able to do that kind of math. And when I say very close, I mean really close. Like, rocket science isn't all that hard, actually. You know, I mean, like, we're right near the math we need to send rockets into space. Okay. Do you have any questions right there? We've been to the moon and back during this lesson already. We went out there to the cycloid and we went out to Pluto, and then I brought you back down to Earth and go, okay, this is more like what we're going to be asking you to do right now, parametrics. Sub in t values to get x and y's and draw them. Okay? No big deal. Oh, there's the curve. Connecting the dots means we understand that all the t values in between are used. We don't need to sub every single one and say, okay, I got the gist of it here. And actually, I'm unhappy with this slide because I think it needs one more thing. And you should add this to your note, is an arrow on each one of these ends to say, and we keep going from there. This says negative infinity to infinity. Now it says sketch the curve for negative 2 to 4. Oh, let me just think about that for a second. Okay, it asked for a negative 2 to 4, so I'm wrong. And how do I get rid of these now? Eraser. Ooh. Oh, that works now. PowerPoint used to be terrible at that. Okay, but if we were doing negative infinity to infinity, we definitely want the arrows in there to say this thing goes on forever. Okay. Now, if t represents time, t greater than or equal to 0, which it often will, t will be time, in what direction would the particle be moving? Oh, this is just like a question on the test. I'm going to really try to do that for the first couple of chapters. I'm not normally that kind. It's not my job to be that kind. It's my job to get you ready for university. But Corona, advanced functions online, there'll be times when I'm like, and there's profs out there that are wonderful at this. All of a sudden you'll see their energy level come up and they'll go, oh, this is cool. Check this out. Get your highlighter out, your red pen, and go, this is going to be on the midterm. Yeah? Or has it got a great chance of being on the midterm? This type of question where it's asked, which direction do you think this thing's going? Is a question I definitely have used on the test. If t represents time, t greater than or equal to 0, in what direction would a particle be moving? You just have to look and go, well, what are the points? At time 0, it was at 0, 1. So it was here. I need pen again. Pen. So we went here, 0, 1. Then we went to negative 1, 2. Then here, then here, then here. So I can put little arrows in there to remind myself which way we're going. And that would be enough if you drew that on there. Maybe you'd say, oh, it's sort of going clockwise. Yeah? You just describe any way you want to tell me that you know which way this thing's going. You could even list the points. You could say, oh, it goes from here to here. It goes from 0, 1 to negative 1, 2 to 0, 3. You know, something to indicate you know that this t matters in the whole situation. That's where it matters. It might matter in the direction things are being drawn here. That never mattered before, the direction. It was always just make the curve and that's it. Determine a Cartesian equation. Oh, I already gave this hint that this question was going to come up. Cartesian, oh, I want yellow now here. Pointer options. Yeah, I was already. So circle that on your note, please. Cartesian equation. And just say, now we want x and y's. And I'm going to need a separate, I'm going to have to go back to Active Inspire to do that work. And if you've been sleeping through all this because you're used to sleeping until 3 o'clock every day, now's a good time to tune back in, because this is like the first, this would be the first sort of difficult thing I'll do all day that you're responsible for. You're like, oh, the cycloid, that was pretty difficult. I mean, I know you're not responsible for that. That was just me trying to be entertaining math-wise. This, you got to be able to do. Keep those annotations. Switch over to Active Inspire. Oh, I'm going to try and do better than that. New slide. I don't know if this is quicker or not, but it makes me feel like camera. I'm out of practice. What do I want? No, I want this thing here. Oh, yeah. Remember now. 6 months on the bench, and now I'm back in, coach. Yeah? Oh, yeah. Still got it, baby. There we go. You with me? Full attention now? Test question coming up. Get this back to x's and y's. Not always possible, but if I ask it on a test, it means it's possible. This is going to be weird in the video. There's people I have to talk to. It's just remembering my brain. It's not about, it's nothing big, so don't feel like it's something. And Jamie at some point. And Connor, your textbook appeared. I don't know what that means to you. I don't know if I put your textbook in as missing or not or whatever, but I found your advanced functions textbook. It appeared. You might not even know it was lost, but it's here. So we'll talk about it later, okay? Here's the plan. Okay, x. Actually, let me ask you if anyone has a plan here. I've tried to kill enough time. We're trying to take these two equations and get it down to x and y. There's another way to look at that. The other way to look at that is, I got to get rid of t if I'm going to have just x's and y's. That's really what my plan is. Will, what's the plan? Okay, I love some of the things he said. He said solve for t. That's exactly right. And he says solve for t in terms of x over here. He's right, that could be done. Mr. Piccone, how are you? How do I look with my multiple microphones and everything? Not good. Really good, really good. Yeah, things are going well. Okay. I think you probably could solve for t here. It'd be a little bit of work. Will seems confident. He's staring at it like, I could do it. I got it. Which one's easier, though, to solve for t? Yeah, so give it a little thought beforehand, because sometimes this could be difficult or impossible. A little tougher quadratic, and you'd be in serious trouble. This one will complete the square pretty easily. You could solve for t pretty nicely. I'm going to go after this one. Y equals, oh, not y equals, y minus 1 equals t. Yes? And then over here, sub t equals y minus 1 into x. X equals, so the t is y minus 1. Technically, you're done. Making a Cartesian equation means getting it to x's and y's. Success. Now, it's not the Cartesian equation we'd love to have. We'd love to have y's in terms of x's. Okay? And that's going to take some serious work. Okay? So, I'm just going to put a single check mark there going, you're done. They said make a Cartesian equation. I did. It's not an explicit one. It's called an implicit one. And I'm not writing those words down because you're not responsible for them yet. But implicit means it's there. It's there. You got it. You can do it. Whereas explicit means I've actually solved for y. Okay, that's going to take a little bit of work here. X equals yeah? Keep an eye on me. I'm out of practice. Oh boy. Solving for y by itself. I already said out loud what's got to happen here to make this happen, but is anyone following or know what has to happen if I'm going to actually solve for y by itself explicitly in this? Math is taught so weird in high school. We throw things at you randomly that don't seem to matter at the time, and then they come up and pop up to bite you later on. I'm going to have to complete the square in this thing to be able to isolate y. So here I go. You can ask questions as soon as I'm done this if you want. Y minus 2 squared. Yeah, it's good. Minus 4 plus 3 is minus 1. Okay, so now I'm ready. X minus 1 equals y minus 2 squared. Plus or minus square root x minus 1 equals y minus 2. And then finally, plus or minus root x minus 1 plus 2 equals y. Ooh, that is some nutty algebra on day. Feels like day 1 to me, but it's actually day 2. I want to note one important thing in that. The algebra you can look at later. You can ask me about it. You've seen this algebra before. You got to brush up on it a bit. You'll be a bit rusty. But this plus minus thing. Why is there a plus and minus there? We really got to get to the root of that, he said, enjoying his stupid math joke. What is it about the situation that makes it I need a plus minus in that solution there? Josiah. Yeah, square root's got a major league problem to it. Yeah? Take a look at this very, very simple equation. X squared equals 25. My 7-year-old daughter, and you at 7, I could probably explain to her why one of the answers to x squared equals 25 is x equals 5. Because 5 times 5 is 25. And she'd go, okay, I get that. But to get to plus or minus 5 needs a lot more work to go, because this is an important moment here, because that's a 2, or any even power, the negatives will work as well. You get this extra solution in there. It has to do with the parabola having 2 sides. You can have 5 over here, or you can have 5 over there. You can do it on both sides. It doesn't do that for odd powers. You don't have to worry about that. You don't need that plus or minus for odd powers. It's on one of your practice tests where the plus or minus doesn't come out because it's a power of 3. It was on the test last year and it burned a couple of people because they put plus or minus automatically for a cube root, but you don't need to for cube root.
Hello.
How are you?
That's in grade 9, no calculator.
Oh, well, there's bins over there. I think that everything is in there because we picked through and took everything that was not the greatest out of there. I think everything that's in there is very nice. And none of those are SJCs, by the way. Those are all found in lockers and so on. The SJC supply is somewhere else. Your favorite $12 calculator?
It's good for $12. It's really good.
Amazon had the Casio FX 300ES on for $12 for a while, so I stocked up on those babies. Oh, I was wound up, let me tell you. Not as wound up as when I order new Rubik's Cubes. That's a big day at the Todd house when the new Rubik's Cubes show up. What's that? I think my eyes smile permanently now. I look in the mirror when I smile and don't smile. I'm like, oh, those are the same wrinkles either way. That stinks. Oh. Well, I did all that to give you some time. What questions do you have on this? Check my phone. See if someone's texting me and going, are you nuts? I'm going to say that's just completing the square. By just, I mean you've seen it before, so don't freak out. Just get it the details worked out. Yeah? Not like the cycloid, which was something all new. Emmett, question. Oh, did I make a mistake? Here, where to go? Oh, this one moved over, and that's a plus 1, yes? Do we agree here now? Okay. I never did check the PowerPoint to see if I matched up with the PowerPoint. How did I do? Plus or minus positive 1. Positive 1, positive 2, yeah. So when I move that negative 1 over, I miss switching that over to positive 1. Happens all the time. And you know what? And when that happens on tests and stuff like that, just don't be too hard on yourself. You really ask yourself when you get a test back, do I think I'm going to make this mistake again? And if you think, oh, that was just silly, forget about it. Stop worrying about it. If you look at it and go, that was a mistake, but as soon as I see it, I understand now why I did that wrong. Don't give that much thought either. Don't be too hard on yourself. But if you look at a mistake and go, I don't know why that's wrong, that's when you start to worry, okay? Little mistakes are going to happen. The idea of, in this course, you might set your goals at 98, 99, 100, but that's not really the long-term goals in most courses, to get 98, 99. You're going to have those little mistakes. It's going to happen. Other questions from this? That was exciting. I saw some nods going, yeah, okay, I'm sort of with you. And then the only question we really had was a correction. It was like, no, you had to fix that there. Huh? I don't think the one I put in the test was even that difficult. Yeah? But you're going to be asked to do that, for sure, to say, oh, here's parametrization. Get it back to Cartesian. You can put a big red star on there. I'll bet you $10 it's on the test. I've got the inside information. Yeah? You're going to have to be able to do that. Yeah? I want to tell you on the big picture on the plan today. This is a long lesson. In regular school, it's a 2-period thing. First period, teach it. Second period, do the work. I'll take a vote after I'm done here, how you want me to handle it. I've got 2 other lessons to do today. I could do them both in the afternoon. One's on logarithms and trig. One's on functions. It's all stuff you've mostly seen before. It'll be a little more familiar than this. So I'll do both those this afternoon. Or I could go ahead and teach again at 10:30. It depends on how you want to approach that. We got time to worry about it. Where was I? From current slide. Last time I did that wrong. I went back to the beginning. Is this what I just did? Yes. Did all that? Yeah, okay. And I did this, and I did that, and I got it right finally. Then it's help. Good? Another example. Consider the following parametric equations. X equals root t, y equals t. Hopefully we're experienced enough now in parametric equations that they look really weird, but you go, well, I could get the curve. I could take t values, this time only t values greater than or equal to 0, sub in 0, 1, 2, 3, 4, and hopefully figure out what the heck is going on here. Determine a Cartesian equation for this relationship. The nice thing here is t's already solved for. T equals y. I didn't have to do any special work to solve for that. So I can just take this t equals y and sub it into here. And instead of x equals root t, oh, they went after the x. Okay, in this PowerPoint they went after the x. You'd get the same thing if you went the other way. In this PowerPoint they said, okay, solve for t here, which means move the square root over and make it squared. Well, my laser pointer again. I just enjoy that. Pointer options, laser pointer. Okay, so right here, well, not that one, this one. Yeah, there we go. Okay. This root moved over here to become x squared, so I get t equals x squared, and then I could take that t and put it right in for the y. Y equals x squared. You're like, hold on. You went through all that to do y equals x squared? What am I, in grade 10 here? The reason we practice on easy ones is because parameters are new. Let's practice on easy ones. Lines and parabolas and so on. Then we'll be more ready for tougher ones. But it's not the whole parabola, actually. Why is this particular situation not the whole parabola? I know it says y equals x squared, and you're like, oh, that's a parabola. I'm like, I know, but something's wrong. Well, x is only the positive root of 2. The t value is only greater than 0. I'm only going to get the one side of things here because of those two situations. So the y equals x squared, but the x values are only greater than or equal to 0. How do we know that this domain restriction exists? Right there, t greater than 0, but also x is only positive root of t. We're not getting both positive and negative values of x, though. Use the graphing calculator to graph the curve from its parametric equation. From its parametric equation. Get out your calculator if you have it here. If you don't, do not panic. I'm going to do it on the screen. Okay? And I think my calculator does these things pretty well. Because what I wanted to warn you about the calculator is that, again, this ROM that I've downloaded for this particular calculator isn't perfect. It has a few things a little different than your calculator, so don't freak out if what you see on the screen isn't exactly the same as what you have on your calculator. Move that over there. Do I have that set up just right? Yes, I do. Okay. Stick with me, and as soon as you get lost, don't let yourself get 2 or 3 steps behind here. Yeah, when you're doing these calculator things. As soon as you're 1 step behind, put up your hand and go, no, stop, whoa, let me do this. Okay, so menu, 5 for graph. And these are all y equals. You're like, well, we're only going to put the x. Get ready, big moment here. Down at the bottom, select, delete, type. Yeah? Hit type and watch what the choices are. You can have y equals, which is the mode you're used to. You can have r equals, which we haven't covered yet. That comes much later. And then Parmesan cheese there. I don't have enough letters to do the whole thing. You got to know that that means, it's like intersection yesterday. What was intersection? ISCT or something weird like that. Parametric. Now watch the screen. Watch my screen when I hit parametric. Watch what happens. It's so good. It doesn't say y's and x's anymore. It says x's and y's. And it's got a little t there saying, oh, you probably want these in t's. Again, if you're like, can't we just use y equals x squared? Yeah, you can. If you want to stay in grade 10 academic, go ahead. You want to move towards cycloids and stuff like that? We've got to learn about how to deal with these with parametrics. Okay, so x had to be root t. So find your square root button. I believe it's over top of squared. So you hit shift squared and you get a square root. And then hit this x theta t button. And it's so good. This button does whatever for the situation you're in. Yesterday when we pressed it, it said x. When I hit it today, it goes t. It goes, oh, you want t's today? I'm like, yeah, I sure do. So I got x equals root t. And then for the y, what is y? Oh, just t. Am I drifting in and out of great sound here? I feel like I'm not as loud as I was before. Is it good or no? It's good, Veronica, it's good. Okay, so y equals t. Enter. Okay? That's simple. You got to switch over to parametric for your type, and then enter the two equations as given. Then hit draw. And if you think something's missing, good. I'm glad you know something's wrong here. Okay? Not wrong. Missing. Yeah? I'm going to hit draw, which is the F6 button over here. Again, just to refresh you, when they got these little menus at the bottom, they mean use the F keys to get those things to happen. So when I hit F6, I bet you that's not what you get. You got the whole parabola, didn't you? Well, yours isn't even on the screen. Okay, this happened yesterday to some people, that the window would go all over the place. Here's several things to do when you go to draw and it's not where you think it's going to be. First move, if it works, is to go to zoom, which is the F2 button, and hit auto. And sometimes auto zoom goes bang exactly what you want. In this particular case, it didn't do exactly what I wanted, because now I can't see the whole parabola or where the whole parabola would be, yeah? So then the other thing you can do is V window, which is the F3 button, and then you can make the window whatever you want. So for instance, I'm going to make the window, I always go negative 10 to 10. When I don't know what the heck's going on and I can't see my graph, I always go negative 10 to 10. That usually solves my problem. X min negative 10, X max positive 10, and then Y min negative 10, Y max positive 10. This is the one part of this calculus that's sort of old school. You're like, I actually have to set up the window like this? You computer coding people might actually have to deal with this, where you got to make your window sizes yourself and everything like that, but the rest of us are like, oh, can it just do it? And then exit to get out of that, and then draw, and then you should get your graph there. You only got half the graph? Okay, good. Simon? Nancy? Root T and T, that's right. And then exit out of there. Draw, range error. I'm going to try something, okay? Oh, actually, I'm going to go window, not open. I'm going to go F2, F1, delete those, and start again. Draw, range error. Wow. Yeah. Did you go 50 and negative 50 that there? Okay, so we got to get back into there because you got to go. Yeah, because it doesn't let you get back there without actually drawing something, does it? I'm going to try menu and go down to system and go down to F5 for reset and main memory. Exit, exit, menu, 5, type, what was it, root T? Root T, T, enter, draw. Okay, important little thing here. Simon punched something and things got wild, yeah? And he couldn't get out of the error message and he was trapped. So if you're ever trapped like that, go to menu, go down to system, and reset the main memories. And then things will go back to the start and you'll have to redo it, but at least whatever you did wrong will be erased. Because sometimes it gets in a little loop there and has trouble. How are we doing? Were we good? All's well? Circles. Quick review of grade 10. Recall that a circle centered at the origin with radius r is given by x squared plus y squared equals r squared. This equation is easy to remember, actually. We used to do an activity in the cafeteria when I taught grade 10 academic. When was the last time I taught grade 10 academic? 17 years ago. We'd go down to the cafeteria and ask everyone to stand. We'd actually set up a grid down the cafeteria and say, everybody stand on a point where x squared plus y squared equals 5 squared. And they stand on it and they form a circle. Then we'd go over and we'd do the activity again and say, okay, everybody stand so that you're 5 meters from this spot. And it was the same thing. You get the same curve. A circle, in reality, what a circle is everything that's the same distance from the middle. Obvious, right? Well, that's what this is. It's a Pythagorean theorem. It's saying, make sure your distance, x squared plus y squared, is the same for everybody in the group, and you'll get a circle. Yeah? There it is right there. If we're all going to have the same x squared plus y squared, we'll all be the same distance away. Pythagorean theorem. So what is the center and radius of a circle with the equation x squared plus y squared equals 49? When it's like this, x squared plus y squared, just like that, it means that the center's at the origin. 49 is the number over here, that's the r squared, so we're talking about center 0, 0, radius 7. How would the equation be different if the center's not at the origin? Well, you just shift it, just sort of like you do with regular transformations. So if you've got a circle with center 5, negative 3, and radius 5, just stare at that for a minute and see if that exactly matches up with what you're used to with transformations. The 5's in there, but because it's inside brackets, it's the opposite sign, minus 5. And then minus 3, because it's inside brackets, it goes back to positive 3. So that's how you deal with circles not centered at the origin. You might not have seen that since grade 10 academic, and some 10 academic teachers actually gloss over it, they skip over it sort of, so you might, anyway, you got it now. Questions about circles? Okay, big fun coming up here. What do you want to do here? We go into a whole bunch of investigations and examples now. We could take our 5-minute break now to avoid other people's 5-minute break, or I can press on, and I think it's about 25 minutes or half an hour I got left, and you get your break a little bit after. Which is better for you? Press on? Press on, we say. Okay. Get your calculator out. You already had your calculator out. And delete the ones that are in there. So watch me delete what's in there. I'm going to menu 5. F6 gets me back to the equations. And if I hit F2 for delete and F1 for yes, so it's just a little F2, F1 sequence. That's the one I do have memorized. Of all the little sequences, I know how to delete a function. F2, F1, boom, it's gone. And they want me to put in a cos t, a sine t, but let a equal 1, 2, or 3. So for the first one we're going to put in 1 cos t. And the second one we're going to put in 1 sine t. I could have put in 2s or 3s, and I will in a second. And then it says, in a square viewing window, using the parameters 0 to 2 pi. I don't know what all that means, but I'll get to it in just a second. When I hit draw, do you get this little picture like this, something like that? The problem is it's not a square viewing window. It's been stretched, and so it looks like a little oval. So, hit zoom, and there's one on the second screen that says square. Can you see the little SQR there for square? It'll give you a nice square viewing window. Now, you see how it's really small there? Mine, maybe yours is perfect size. You know? Hit zoom, and I'm going to go zoom out. Oh no, I wanted to zoom in. Silly me. Zoom in. Zoom in. Have to hit enter after every zoom in. Zoom in, enter. Oh, here we go. Zoom in, enter. Now I know what's coming next, so I'm going to zoom back out a little bit and put it about there. Okay. Now here's the question. Ruben, how are you? We've rearranged all this, so we got a little more space up here. We have one person in front. Okay. Here, big moment in the lesson. You're like, during these lessons, if you're thinking, Okay, I got to focus on the things that I really got to learn from this lesson. This is one of the things you got to know. How to parameterize a circle. Parameterize a circle is cos t, sine t. It actually works if you go sine t, cos t as well. We're going to learn lots about this parameterization as we move on here. What happens if we do it with a 2? Menu, graph, and oops. F6 is the magic button to go back and forth there, and I'm going to arrow over. Oh. Does yours allow you to arrow over? Mine doesn't. Oh, I could arrow to the right first, and then I had to go over. Oh, interesting. Okay, so I'm going to delete that and change that to a 2. And then delete that, change it to a 2. So now I've got 2 cos t and 2 sine t. It's good? Then hit draw, and what do you get? What was different about it? Dead batteries? Oh yeah, go to zoom. Second thing, I'll go to zoom square. Did you see that? This is a perfect drop. I opened up the battery case, just flung it open, and exactly 4 batteries fell onto his desk. It's like hitting 0, 0 on the when you're pumping gas. Oh, you guys even know what I'm talking about. You don't care about how much. Oh, it was actually in there, was it? You forgot you didn't forget it. Okay. So what happened? What did the 2's do? Radius 2 on the circle. I mean, you can do the 3 if you want. Hopefully you get the gist. So, circles. Cos t, sine t, and just put the radius out front. I got that later in the note. That's what we're supposed to be discovering here. Now, I ignored what it said here because I knew what I was doing. But it said using the parameter interval 0 to 2 pi. I don't know what they're talking about. Okay, so I'm going to ignore that for just a second. But I'll fully explain it in just a second. Then it says let a equals 2, which I did. If I hit F6, I can see I've got 2's. And you graph the parametric equations given the following parameter intervals. What are they talking about? This is, I'll nominate this as the best part of the lesson for the morning. What's going to happen here? Go back to draw and hit V window again. And here's the V window they've chosen. To make it square, apparently the X has to be twice as big as the Y's. To make it a square viewing window. Otherwise it gets stretched out a little bit. Yeah? So when I chose square, it went double with the X's than it was with the Y. The reason that is look at the screen's doubly wide as it is tall. If you make them X's and Y's the same, you're going to get things stretched out. Anyways, you don't have to know all that. You just got to hit square and start off with a square viewing window. And I'm just going to scroll down here and see what else is down here. I've got X min, X max, I've got scale. We won't really use scale at all this semester, but when things have a lot of dots, maybe we want more dots or less dots, so we'll adjust the scale of the dot, that's fine. Check this one out. T theta minimum. This tells it what t value to start at. And I told it to start at 0, or it automatically chose that. But it's telling me don't start at 0, start at 0, but end at pi over 2. So when I go down, it says t theta max. Now look, lots going on here, lots of trig here on the first day. T theta max is 6.28. 6.28? What the heck is that? Why 6.28? Damn it. It's 2 pi. It knew as soon as I put in sine and cos, it goes, okay, I'm going to put 2 pi in there. Probably you're going to want 2 pi. Why is 2 pi so important? 2 pi is one full curve in radians, 360 degrees. So it chose 2 pi up top, but this time it wants only 0 to pi over 2. So I'm literally going to type in the max there, pi over 2. I've forgotten where my pi button is, and I can't read the screen here. Oh, I remembered. Pi, I'm actually going to write pi divided by 2 in there. It accepts that as an answer. And that's what it told me I was to do there, was 0 to pi over 2. So 0 to pi over 2, enter. It goes to 1.57. I'm going to exit out of there and check this out. If this doesn't enthuse you, then you can turn in your nerd button right now. What just happened? Why is it different? It went 0 to pi over 2, and then just didn't go the rest of the way around. So now we have control of how much of the circle we get. We never had that kind of control with Cartesian equations. Parametric equations let you control exactly what the heck is going on. All right, so if I go 0 to pi, what do you think you're going to get here? Half the circle, yeah. So V window down to the T theta max, and I'm going to go pi over 2. Pi over 2, there we go. Enter, exit out of there and draw it. Oh. Un momento. V window, not pi over 2. The second one was pi, right? So, pi. Enter, exit, draw. Ah, now you can have any parts of the circle you want based on the t's that you choose. How is that all working together with sine and cos? How is this also a circle? Okay, I get to that. Show algebraically that this is the equation of the circle. I'll get to that in just a second. Let a equals 3, play with those intervals. I encourage you to do all these explorations and try these out and see what you get. And you'll have forward drawing circles, you have backwards drawing circles, you have this part of the circle, that part of the circle, different radius. Those are all good things to try and get to know how this all works together. Question? Yeah? All right, let me take a look. 2 cos t, 2 sine t, draw. And then one thing I'm going to try whenever I get lost, I'm going to go zoom, auto. Oops, that didn't work at all. Zoom, square. V window. I'm going to go try -10. To 10. Oh, look at how small the y's are. For whatever reason, I don't know why they got so small. -10 to 10. Exit, draw. Oh, still not there. Okay, let's try this then. Exit. F2, F1, get rid of that. And then I'm going to try and just go cos t sine t. Really start over again. Wow, that didn't work either. Scale, dot, pitch. All right, here I go. Here's my big move. When some setting gets messed up and I don't know what the heck it was, reset, main memory, yes. And then just start the procedure over again. Okay, so I do want you to do the rest of that exploration. I wanted you to get you started on it because I remember from last year, getting started on it was a bit of a problem. But that's one of the things to do. Geez, when are you back with me? The 21st or something like that? You go for the big break now, okay? All right. I'm going to go ahead and do some of these examples. Example. Show algebraically that the parametric equations above represent a circle centered at the origin. What? What am I going to do? Okay. New page. No, just like this. What does the Cartesian equation of a circle look like? I just talked about it. It's not that far away in your memory and in your notes. But if you want Cartesian equation of a circle, what do we got? X squared plus y squared equals r squared. Apparently, somehow, some way, this is the same thing. Well, if we're going to have Cartesian, we need x squared and y squared. So that's how I'm going to write here. I'm going to write x squared plus y squared. That's what it's supposed to come out to. It's going to be a circle. Now here, though, the x is a cos t. I'm going to make a mistake on purpose here to see if you're with me. And the y is a sine t. What did I forget? Squared. So really, the x, which is a cos t, is squared. The y, which is a sine t, is squared. So everything's squared. So I'm going to put the squareds, distribute those squareds in there. A squared cos squared t plus a squared sine squared t. Even if you're only off for the summer, 2 months, and not off since coronavirus, I would still say the same thing, which is give your brain a chance here. When I do crazy stuff up here, give your brain a chance to get all this stuff back in motion. Like common factoring. Do you see a common factor between these two things? It's a squared. And I'm left with cos squared t plus sine squared t, which I'm going to highlight, really just to kill time to see if your brain triggers. Cos squared t plus sine squared t. Brain working. What's cos squared t plus sine squared t? What's that? It is a trig identity. It's maybe the trig identity. It might be number 1 on the list. Another math joke there. Cos squared plus sine squared is 1. Always. If you have the parametric equations a cos t and y equals a sine t, what you've got is x squared plus y squared equals a squared, which is the Cartesian version of it. They had to transfer back and forth. It had to work. The two forms had to be equivalent. They both make circles. And it does. With another little trig identity in there. So in the middle of trig identities last year, I might have been like, this is stupid. When are we going to use this? This isn't important. I'm like, I know, we're just practicing. You're going to need it. So we'll just practice with it a little bit. But again, as I promised, when those identities come up on a test, you'll still have this, unless I warn you. It's like chapter 6 or something like that. I go, okay, I'm not giving you them all. I'll give you these ones, but not these ones. You know, we'll work it out then. But for now, you got this available, and maybe worth printing out or finding in your old notes, or text me to post it, getting that trig toolbox ready in your book somewhere when you need it. That was question 1. Any questions about question 1? I forget where we were. Let me find it. 2. Consider the following parametric equations. Describe the shape of the graph determined by these equations. I'm going to do my copy and paste trick again here. I'm tired of looking back and forth. So here I go. Tools. No, not that. This one. Yes, like that. Do, 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 do. Okay, that's good. Go over there like that. Here comes number 2. Current page. Return. Do we get past the break yet? We are past the break. Break? Sled on. Break? Yovan just got here. He's like, what break? It's been a whole break the whole time. One more, then break? How about that? Good compromise? Consider the following parametric equation. Describe the shape of the graph determined by these equations. On your test, there'll be 2 parts to the test. One part where you can't have this calculator. You've got to answer the questions without using the calculator. You'll see when you get the sample test. And there's another part where you can have the calculator. And a question like this is completely different depending on whether you can use your calculator or not. You can use your calculator. Just punch it in the calculator and say, hey, what is the shape? But you're supposed to know. You're supposed to know. No, you're not supposed to know it yet. Hopefully I just taught it to you. What will this be? If I graphed 5 cos t, 5 sine t, what shape will I get? There's 2 parts to the answer. Anyone got a What shape is it going to be? It's a circle. I'm going to write over here. Circle, radius 5. That's almost the whole answer. There's another part to the answer, though. Oh, good. 5 cos t, 5 sine t. That's the investigation we did here. When we have something cos t, something sine t as the two parameters, it's a circle. You're like, well, how was I supposed to know that? Well, that's what that investigation was for. I know when you do more of that investigation, you get used to that when you just see cos t, sine t like that with, big moment, the same number in front of both of them, that's a circle. What if the numbers are different? Yeah, I'll get to it. Don't worry. It's coming up. Circle radius 5, but there's a comma here. There's something more to this whole situation. Yeah. I'm going to put semicircle. It only goes from 0 to pi. And you might be confused at first, which half do you get? You can sub in points for that. Even without your calculator, you can sub in points to see which points you're getting. Okay? Knowing for sure which way it goes, I don't know if you memorize that. It might be tempting to memorize it, but if they go sine cos, or if they put a negative in there or something like that, it can change the directions all around. So I don't know that I would assume that I can just memorize and know what that's what's going to happen. Determine the initial and terminal points. B. Initial. T equals 0. I get x equals 5 cos 0, which is, let's see, cos is 0. That's not on the trig toolbox. Even your regular calculator knows the answer to cos 0, though. But I really hope that the cosine graph is something that will be in your brain, ready to rock and roll as we get rolling here. Cosine normally starts at 1, then comes down and up. So what I get is 5 here. And then I get y equals 5 sine 0. Sine is 0, 0. So I get the point 5 comma 0. That's the initial point. If this thing went to draw the circle, it would start at the point 5, 0. And then the terminal point, t equals pi. This might be asking too much on the first day back. Okay, I know the other day was the first day, but this is the first day we're actually really cutting into some math here. Cosine of pi. Let your brain work. Cosine normally starts at the top of the curve. And after 2 pi, it's back up to the top of the curve again. So where is it at the halfway point? At the bottom. And the bottom is negative 1. Please do not freak out if that information is not in your brain at all. Use that as motivation to go, yeah, it's handy having that kind of information in my brain when I'm dealing with cos and sine. To be able to go, I know where the 1s and 0s are negative 1. Oh, I'm snapping my fingers like it should come up like that. No, I don't think it should come up like that. I think it should be like, Your calculator's there. It's handy to be able to come up with those things. And then what? A sine of pi. Let's see. Sine starts at 0, goes up and down and around in 2 pi. So after half a loop, it's at 0. So if we are going to draw this circle using this parameterization, it starts at 5, 0 and ends at negative 5, 0. We know that's what it does, but we just don't know, is it this one? Or is it this one? Here's part C. Oh, stolen right from my test. No, my test stole it right from here. Determine the direction in which the graph is traced. How many more points are you going to need? One more point will do to decide which way we're going to go. Sub in t equals between 0 and pi. Any number will do between 0 and pi. Pi over 2 would be a great choice. X equals 5 cos pi over 2. Cosine of pi over 2, 0. Your calculator's there. As long as it's in radian mode, you can handle this. Not just your fancy new calculator. Any calculator can handle cosine of pi over 2 in radian mode. And then, I'm just going to draw a line here. Don't want these to get confused. Y equals 5 sine pi over 2. And sine of pi over 2 is 1, so I get 0, 5. My middle point is 0, 5. Okay, initial, middle, 0. I know it doesn't look much like a circle. Do we agree it's heading that way? Initial, middle, final. Which way? Oh, you could describe it to me. You could draw a little arrow showing me. You can do whatever you want. I'm just going to say counterclockwise. Am I starting to sound like Darth Vader reading on this thing? Last one, then we'll take a break, okay? Determine the Cartesian equation. Okay, two ways to know the Cartesian equation. One is I've got it memorized. I know what the Cartesian equation is for a circle. The 10 academic kids could come in there and rhyme off the Cartesian equation. Once we explain what Cartesian equation means, they just know it as the equation. They don't know there's different types of equations. I want to take a shot at it, though, going, oh, how do I get there from here? What do you got to do with these two things? If they got coses and sines in them, how's that ever going to come together? How are we going to get rid of cos and sine? It seems like it's impossible that it would ever go away. Square them both, yeah. That's the higher level version of understanding this. Is go, oh, this has got to work at some level. X squared plus y squared is 5 cos t squared plus 5 sine t squared. I really wanted to put this on the test. Force you to have to do this. And you can. You could answer a question like this using this. I didn't do it because I was really trying to be kind in the first test, yes? You can just memorize it and you can go, oh, I know the answer. It's x squared plus y squared equals 25. Because cos squared t plus sine squared t is 1. But I really want to tie the trig in there too, so you get a picture of what the picture I couldn't show you very well in advanced functions, not just because of COVID, but because of the material that was there, that left trig being, oh, who cares about trig? It matters even in something that doesn't seem to have triangles in it. It does have triangles in it. You have questions? Folks, all the way through this course, in this quadmester things, I'm going to change my plan all the way. I don't know what my plan is for the rest of the day. I don't really care. I'll teach until I'm out of gas or until you're out of gas. Away we go. There's 2 other lessons I'd like to teach. This one isn't even over yet, but I want to give you work time, so I'm going to balance all that out before the day's over. Take a 5-minute break and we'll start back. Listen to my words carefully, folks. Question? Oh, yeah, good question. Cos t is all one package. That t is buried inside, really. It's not like other functions. It's cos of t. It's not cos times t. If it was cos times t, then when you squared it, the t would get squared as well. But that whole thing travels as a unit. The t's buried inside, and I can't really get to it. Log and ln work like that as well. E to the x will work like that. There's other functions that work like that, where that t is actually inside the whole thing. Good question. Okay, so my words carefully so you understand. 5-minute break. I'm going to start back up to finish this lesson at 10:45 by that clock there. Okay? On the break, you can't be wandering around. You can sit down, get a drink, take off your mask while you take a drink. Just relax for 5 to 10 minutes. You can go outside. It's a cool day, so it's a nice day to be out there, and take a little walk, whatever you like. Okay?